Log into almost any online course today, and you will find an endless vertical wall of generic document icons and video thumbnails. We have engineered digital environments that are incredibly rich in content, yet these exact spaces consistently produce passive, rote learning. Instructors often see poor results when they transpose the didactic strategies of a physical classroom directly onto a digital interface. This broad brush approach to explanatory content relies on a cold cognitive presentation, ignoring how novices actually process new, complex information without adequate context. In fact, researchers observe an expert reversal effect, where highly structured, dense presentations only benefit individuals who already possess significant background knowledge, actively alienating beginners. In a rigorous digital environment, instruction focuses on the specific ways a student engages with the material, rather than the volume of information provided. The designer's task is to engineer precise, intentional interactions that move the learner from passive observation to active use. Shifting the LMS from a filing cabinet to a behavioral environment provides the structural support needed for deep cognitive processing. To fix this lack of engagement, we have to start from a blank slate and take a systems engineering approach to course design. This diagram shows the 5 interconnected factors that dictate all effective digital instruction: learning objectives, learner characteristics, content type, instructional strategy, and technology affordances. A stable interaction requires that the learning objectives and the specific type of content dictate the other variables in the system. But a common failure occurs when situational factors, like the specific features of a new software tool, are allowed to dictate the instructional strategy, breaking the equilibrium. To maintain this structural equilibrium, designers execute 5 specific pedagogical shifts, beginning with the challenge of fragmentation. Novice learners lack the mental models required to automatically connect disparate readings and videos into a cohesive neural network. The engineering solution to this binding challenge is called the pedagogical wrapper. Before a student engages with the material, the wrapper must explicitly state 3 things: what the material is, why it is relevant, and exactly how the learner should approach it. Stating this explicit pedagogical intent upfront primes the learner to cognitively integrate the new data points with what they already know. Compare this targeted integration to the common practice of dropping a 60-minute recorded lecture into a module without any context or guidance. Because novices cannot naturally perceive the structural matrix of a discipline, the instructional designer has to explicitly build these cognitive bridges for them. That brings us to the second required shift, moving away from broad brush explanatory content and toward finely targeted information. Decades of data show that passive interactions with purely explanatory material generally produce the lowest learning gains. Explanatory material only succeeds when it is rigorously carved down to target complex concepts that directly support higher-order problem solving. This forces a third shift, moving from decontextualization to contextualization. Abstract knowledge presented outside of a situational model remains inert and unusable. Designers structure this context using the 7 C's framework: challenge, context, characters, content, choices, consequences, and connections. This interface shows a practical application of the framework in a digital scenario about small-scale dairy farming. The abstract learning objective is grounded in reality. The context and characters are explicitly mapped into the interface through a concrete scenario involving a local cooperative. Instead of passive reading, the student is forced into active behavioral engagement. They have to make specific choices by selecting which questions to ask the farmers. The consequences of those choices are immediately reflected in the farmer's response, providing direct feedback and deeper learning. This interface design prevents the student from simply memorizing facts by forcing them to test their situational judgment. An interactive case scenario like this entirely replaces the need for a traditional recorded lecture on the subject. Contextualization transforms inert data into a vital tool for immediate survival and progression within the learning scenario. The fourth shift moves away from single media silos and toward hybridized media content. Many digital courses still rely on an outdated audio-visual text paradigm, where a video lecture, a reading assignment, and a quiz are kept strictly separated in the software. Media hybridization solves this by seamlessly blending formats, matching specific types of information to their most optimal visual or textual medium. For instance, video should be reserved exclusively for demonstrating dynamic processes, but when a student needs to engage in slower, complex conceptual processing, instructional text is far more efficient. This leads to the fifth and final shift, transitioning from purely cognitive dominance to an active interplay with the emotional dimension. Even with perfectly organized content, unmotivated learners perform poorly. Cognitive engagement is fueled by emotional undercurrents. To build this emotional architecture, designers rely on the ARCS model: attention, relevance, confidence, and satisfaction. By using these 4 pillars to induce states of curiosity and introduce moderate complexity, the design activates the specific systems in the brain required for long-term memory retention. The cognitive friction inherent in learning difficult concepts can only be overcome when deliberate emotional momentum pushes the learner forward. If we zoom out from these individual strategies, we can evaluate the ultimate goal of an instructional designer. This diagram illustrates how these factors integrate into the 4 dimensions of learning. Hybridized content stimulates the cognitive axis. The ARCS framework fulfills the emotional axis. Contextualized scenarios drive the behavioral axis. A rigorous module activates these simultaneously, creating a continuous feedback loop. This explains our initial paradox. Uploading a static PDF or a video lecture only touches a fraction of the cognitive axis, leaving the rest of the learning system completely dormant. A massive volume of information can never compensate for a lack of interaction design. Content alone is never enough. In this environment, the success of the online experience is rooted in the deliberate design of the interaction.